Ladies and gentlemen, I welcome you to the ICC 2022 tutorial for Post-Shannon Communications for 6G. My name is Frank Fitzek and I'm with Deutsche Telekom Chair for Communication Networks at Technical University in Dresden. I have the pleasure to give you this tutorial together with my colleagues Rafael Schaefer, Holger Boche, Deppe.
Hello, I'm Rafael Schaefer. I'm the head of the Chair of Communications Engineering and Security from the University of Siegen. I will present the second part of this tutorial, and I will talk about randomized identification, where I will particularly focus on fundamental or information theoretic principles and results. After that, I will continue by incorporating some security constraints, and I will present some first results on secure identification.
Hello, I'm Deppe. I'm researcher at the Institute for Communication Engineering at the Technical University of Munich. I will present the third part of the tutorial. I will talk about the construction of identification codes and deterministic identification.
And I have the pleasure to introduce to you the first part. In all, we will give you 4 parts by 4 different persons. And even though we have only listed 4 people here that are actually presenting, you will see soon that the actual team behind that work is way larger. So let me start with the first part. It's called Medium is the Message. Some contributors from our side is Juan Cabrera, Caspar Lengerke and Ricardo Bassoli. People have done different works in the fields. I will not identify exactly on which slide they contributed, but in all it's a common work together from the chair, but also with the colleagues that you have seen beforehand. The work is a result and also motivated by a current project we have together with the Technical University of Munich. It's called the 6G Live project. It started on the 15th of August in 2021. It's from the budget around 70 million for 6 years, and the main objective, as the name will tell you, it's about 6G communication. So we focus on humans and their communication and interaction with machines, with virtual worlds and real worlds, and we have some certain use cases with special interest on Industry 4.0 and healthcare. And then we will look at key performance parameters for communication networks, which are latency, resilience, security and sustainability. And the subtitle already tells you that we would like to look into something what we call digital sovereignty and digital transfer for Germany. And Post-Shannon is one of the topics, besides maybe also quantum, that is a new technology that we would like to introduce into the 6G Live context. Before I start with Post-Shannon, let me just introduce you the evolution of communication networks. As I'm coming from the chair of communication networks, this is especially something interesting for us, but it also will break the ground for later introduction of Post-Shannon. So here you see 3 different types of communication networks. And on the left, you see the good old telephone network, connecting places with each other with a highly intelligent networks. That was then replaced by the internet design, what you see in the middle here, where we have more or less a dumb network, a very distributed one, and where the intelligent is sitting in the cloud or in the mobile devices, as you can see in the picture. Here it's a network that is more supporting not only voice as before, but also data services. And as you can see here, the aim when we build new communication networks is always to fulfill a certain purpose of the communication network. Now, the future is a network that is intelligent again, but also has some potential of computing within the network, right? And this kind of softwareization of the network is the key ingredient to open the door and break the ground for Post-Shannon, as you will see later. It's always good to understand on which shoulders we are standing. I brought you here 3 pictures of people that really have influenced this type of communication architectures. It's Claude Shannon. We will talk about him a lot within this tutorial. He not only gave us the limits of a communication channel, he also introduced the unit of a bit, right? There's even more, and you will hear about this in a minute. The guy in the middle is maybe the most unknown one between the three. It's Paul Barron. He really designed the internet architecture, describing this in 11 chapters in the 60s, introducing, for example, resilience questions, cost questions, energy questions for such kind of communication networks. And on the right we have Alan Turing, who is then responsible for all the computing that we will need within our networks. The things that you can do when you have softwareization is the way how you, for example, build resilience, right? Or even how you reduce latency. Here are two different things. For example, introducing resilience in communication by multipass, introducing resilience for storage by having distributed storage, and something that we currently looking into is how you also can do distributed computing based on a code, right? The approach we have here is called one code to rule them all. So if we then go back to 6G, there are, for us in the 6G Live project, four cushions that we have really to look into, right? One is the novel architectures, and I have simply described you this and with a simple evolution of the network architecture. There's a little bit more than that, as you will see later. For example, coming from the 5G development, we had 4 generations before. Now we are at the point where we have 5G release 15. And what is interesting, it's not that we are continuing simply with more releases. You see already release 16, 17, 18, 19, and 20 here. That will give us more flexibility, for example, in latency, in new functions like device to device. But it also has new architectures such as island solution like 5G campus solution. Especially here in Europe, we are talking about this to create our own 5G solutions, for example, for the industry, for medical departments and so on. And what you see is also the same happens in the 3D networks or high altitude platforms. And all of them, and we did not depict it here for the cellular networks, are now going also for the open radio access network. So when you talk about 5G, you will have in a cellular network two very important components. One is called the core, the other one is the radio access network. And the core is already now fully realized in software. But soon also the radio access network will be realized mostly in software. And this is really the introduction point where Post-Shannon will later be placed. All of that might be come to a new form that the people call 6G, and this has to be discussed where and when this really happens. For us, 6G is the definition is that we would like to look into something that are future communication networks and that are fulfilling a certain task. While 5G was more machine-to-machine type communication, 6G is looking into human-machine cohabitation. So beside our 6G Live project in Dresden, we have also together with TU Munich an excellence cluster on the tactile internet, really trying to understand what human and machines can do together, right? I will not go into this detail. I have done some IEEE tutorials on this already. Now let's look into the third cushion, which is Post-Shannon. And you might ask, what is this Post-Shannon? I already told you that Shannon gave us some limits that we should respect, but you will see and find out that there's something beyond this Shannon capacity. And as a starting point, a prelude, I'm referring here to a book that Weaver and Shannon wrote together in the 60s. And they talked about how to convey information between the sender and the receiver. And there are different ways of doing that. So they called it level A, B, and C. Level A is the technical problem, something that we currently have realized, and that is normally what everybody is talking today. Well, the thing is how to convey a message from the sender to the receiver by looking at the symbols in the communication. So we assume that by transporting the symbols correctly from the sender to the receiver, the job is done, right? Whether the receiver is actually doing what we wanted him to do is a different question, but this is had never been a question in level A. But the whole technical evolution was really based on level A. But Weaver and Shannon already talked about different levels, level B and C. There is the semantic problem, and this is How precisely do the transmitted symbols convey the desired meaning? So maybe it's not so important that the symbols are correct, but is the meaning of what we wanted to convey to the receiver, is this conveyed, right? And even that is not so interesting. The most interesting question is the effectiveness problem. Is the receiver actually doing what we wanted him to do? So will he do what we wanted him to do? And this can also be that we are sending totally incorrect symbols, maybe even the meaning is not correct, but the action that the receiver will perform is the one that we wanted to have. So there are three different levels of looking into the problem. Now, what you will see here is a shift, a paradigm shift, how we really look at the communication. Before that, we had the sender that said, I want to send a message A. And the receiver only asked what message was conveyed over the noisy channel. So what did Alice send? That is one possible question. This is what we do today. In the future, if you look into identification via channels, is that the sender wants to send message A as before, but the receiver will only ask whether a certain message has been conveyed. So in this case, the receiver is only interested, did Alice give us the message B, right? Like students always ask, they look for one message from the professor, is the lecture over, right? Maybe the rest they don't even are interested, they only wait for the finishing note of the lecture, right? These are two different questions. I personally had a paper on this in 2006. I called it The Medium is the Message. That was really a applied problem where we wanted to convey a message between a set of phones on the one side to a set of phones on the other side. And exploiting the way how we communicate and not actually what we conveyed gave us an interesting point and what the capacity could be in the end. Later we mapped this to CDMA channels in the paper, and that was quite interesting when we calculated the capacity of the system. Already at that time we discussed with colleagues whether it would be possible to go beyond of this Shannon limit. And there was a religious discussion that it's not possible to go beyond it and we should not do that. So we was hiding the message a little bit in the paper. It got accepted, but we never got an award for it. Neither we got thrown out of the conference, right? But already there we thought there is something more, right? And what we do here, I will explain you in a more comic way in the next 30 minutes. That allows you maybe to understand my colleagues in the next three parts. So what is the classical Shannon transmission, right? You have a message on the left that the sender is then putting into a code word, and this code word will be conveyed over a noisy channel to the receiver. The receiver will then receive a code word which is most probably distorted, and from that it will get an estimated message, right? And it will be done in a way that the sender has, in this example on the left, 5 different messages, and we will convey this to the receiver. And each of these 5 messages is represented by one code word, which is deterministically assigned. And on the other side, we have this disjoint and convex decoding of it. If you remember the Hamming distance, that you say, okay, the closer it is to a certain area, we assume it was that message, right? In this case, the sender and the receiver do totally 2 different things. You would say actually that is normal, but it's maybe not if you see what we will do later in the Shannon, in the post-Shannon example. So now go to a new way of communication. We call it the identification codes. So here we have an identification, the ID, that will given to the sender, and he will select random code words out of a certain set that will be then conveyed over the noisy channel to the verifier. We don't talk about the receiver anymore, because when we receive the distorted random code word, we only interested whether a certain ID has been received or is assumed to be received with the outcome of yes and no. So this is really, if you imagine you have a car that wants to know, do I have to brake, yes or no? that is the only thing that is interesting for the brakes. Maybe the steering wheel would like to know, should I go to the left or to the right, right? That is a different question. And what you see then is the sender has now not really 5 different messages. There is a set of code words that are selected randomly, right? How you select these code words, there's a good way to select them and a bad way, right? You will hear about that. But what you already see is these spaces, they are somehow overlapping. And we might ask, is this a problem? So here, for example, the sender would like to send the ID 24, right? So we send it to the other side, and the verifier will look at this and will say, okay, this was inside the green area. So we will say we have verified ID, and we'll say ID is correct, right? So we actually don't decode anything here, right? And we just need an encoding on that side. This is very fast. This is one of the things. But you might ask, why did he really receive ID 24, right? It could be that, or first let me say something about when we do this new approach, what is the advantage, right? In the classical way up here, the number of transmission, capital N, is equals 2 to the power of NR. Small n is the number of bits that we have reserved for the message, and R is the Shannon rate between 0 and 1, right? So this is the classical way. If you look at the identification codes, now the amount of data you can send is 2 to the power of 2 to the power of NR. So double, we are growing a double exponentially with the number of bits that we have here, or the Shannon rate. So this is something interesting for us. So growing double exponentially, you already see where it goes. Capacity-wise, this is a dramatic increase, right? But this is not for free, right? It's always like this. You create something, but you get now a new kind of error, and you have to look into that. Funnily, we already got this error already in the Medium is the Message paper, that we distinguish between 2 different types of errors. One was the error in transmitting a bit. The other was in identifying which channel we really exploited at that time. So you see that theory that we will now explain to you has some meanings already in the real world. So as we said before, there's one example of a correct positive, right? This can happen. It can also be that we waited for ID 58 and we identified 24 and said this is not the ID we are waiting for. So even that is correct. The cross means it was not for us, but green means yes, it is detected in the right way. So we say correct negative in terms of identification. So what can also happen is that ID 21 was sent. We waited for ID 24, but by distortion, we are in a totally different region. And you see here, then we will identify something else and we will have a false negative. It can also be that the distortion is not so bad, but we make the mistake not in the kind of transmission, we make it in the form of identification. So in this case, we would have a false positive in terms of identification. So in the end, we have a hypothesis testing of not yes and no, we should go to maybe and no. So when we look into the error types, you have here 2 types of errors, right? Type 1 errors, they are caused by a noisy channel, and you can reduce them, as you know it already, by Shannon channel coding, right? And you can even remove them by Shannon channel coding, right? But in type 2, because we have overlapping code word sets, you need to find good identification codes, and you can design them in a way. But still, you have 2 types of errors now, right? What does it mean? So let's look into these errors, how we're handling them in a separate way. So first of all, you have the sender ID, you have an ID encoder, and the verifier, which is nothing else than the ID encoder in the same way. And you assume that you have a noiseless channel, right? But what is this noiseless channel in the end? This is a classical channel, Shannon channel. So it looks like this. You have the sender ID encoder, and you have a logical communication with the ID encoder verifier on the other side. So there you see where we have the different types of coding. Above the red dashed line, we have the type 2 errors in identification. And type 1 are the classical errors that you would also calculate in the Shannon theory, as we did in the classical way. So first of all, this identification codes, they can run on classical Shannon systems, right? And you will now see what happens in the sender and what happens in the so-called verifier. And the outcome is then our yes and no, or maybe and no. So the question is now, how do I first create the randomness of the set around my ID, right? So you need some certain local randomness at the sender side. And when you send out the ID, or the code word of the ID to the other side, you also have to explain that you have which kind of local randomness you used for that. So this introduced some extra cost, something that we already know from compressed sensing and also network coding. So how can we deal with this randomness? How to make this cost even lower? One of the things is common randomness. So you have a certain way to create a randomness that is known for sender and the verifier at the same time, right? I will come back to this in the end of my talk. Now, how do I create this kind of message, right? So here on the left side, you say you have certain messages, k different messages that you want to identify, with a different meaning, and this is chosen out of a field size q to 256 to the 8, so to speak, and then you have an encoder matrix. And with this encoder matrix, you create the code words. That is a classical way of doing it, right? But now, what you have, a classical Shannon code word would need to transport n log q bits to the other side, because you have to transmit everything to the other side. What you also can do is, you can just say, I take a random position and just inform them for a certain tag, right? So if you look here, the green space, there are two different code words, the tag 0 and 1, different positions with different meaning. And you just convey the log q bits for the tag and the log n bits for the random position, right? So that is quite interesting. You just don't take the whole code word, you just take one certain position, right? Now, for example, if you have the local randomness, you get the sender tag and the random tag over the noiseless channel. Actually, it's noise, but we assume it's noiseless. And on the other side, you can do then the ID encoder and come up with the yes and no. And this sounds pretty easy. You might say, is the code words, are they so sparse that we can identify it by a single position? So here, for example, it happens that you convey the, for ID 24, you say on position 0, there must be a 17. On the other side, you say position 0, it's a 0. So that would be a different ID, and you say, oh, that's not the same that we expected, but we identified it in the right way. It could be that we go to the same position, and we always go to the same position, sorry, but we have the same tag value. And then, even though they have the same tag value, we are talking about two different IDs. You would identify it as the right ID, but this was wrong. So this is a type 2 error. What you can do now with this attempt is, you make all of these errors. Maybe you will hear later from the other in the group what you can do to make this situation better. Imagine you are not sending only one position, you could even send two positions. That will make your capacity a little bit worse, but you may have more security and you get less type 2 errors. You can find other ways to reduce that. But we currently would like to understand what you can use it for, okay? So imagine that you are in this 6G world and you would like to have the digital twin, which in 5G we already had it, but now it will play a bigger role. For example, learning a robot certain things. And normally, if you do this over distance, it will not work nicely because of latency. What you will do is you create a digital twin, which will be computed in close proximity to you. And when you have a real system and a digital twin, you need always exchange between that, right? And this exchange of information can be really big. As an example, if you have 1,000 states, right, and there even if you have billions of states, you can have 2 to the power of 10 states, which would be state of the art, and then we need 1,000 bits, classically, right? If you now use the identification codes to update in the digital twin, it will, in this case, only need around 10 bits, right? So this is a toy example. You can come up with way more drastic examples here, and you will see how much the identification codes can bring you here, right? And that means the state between the reality and the digital twin is cross-verified with a very few bits, right? And once you have problems in synchronization, then you have to go back and have of the expected full state. That will then take a while. But as long as everything goes fine, you can exploit the identification codes, right? So this is something we have already published some papers about this, digital twin and identification codes, something that we would like really to also realize in the future. Now, the one thing is, how do we really create this randomness, right? So in a classical way is there are tons of these random or pseudo noise algorithm to create randomness, right? There are also seeds for common randomness. Seeds means that you just exchange a seed and then you calculate the randomness on both ends. That's one classical way we also exploit for network coding. We have a lot of experience in that kind of stuff. For example, here you have different approaches for randomness, IETF, for example, or other ones built on Fibonacci stuff. That is something that is currently used also on the Linux machines. So different versions gives you different throughput. And that also has to do with energy and latency. So you would like to have a way to produce this one very easily. So if you do this now for seeds, for example, the same ways that you had here for calculating it, here you are really using the seeds and you see the different speeds, right? Now, let me just introduce you one topic that on 6G Live is also important for them, is quantum communication. And when we talk about quantum communication, there's one thing that we are especially interested in with respect to Post-Shannon, and this is this kind of randomness, right? We will not talk about quantum computing in our project. We will exploit some quantum physical characteristics that are interesting for us. In a nutshell, what we would like to look at is, for example, local randomness, or that is the kind of randomness you can get. Nowadays you can buy some cards to 1,000 to 4,000 euro you have to spend, and then you get a quantum-based randomness, which is quite nice energy-wise, and they could be faster in speed because the pseudo-noise are quite fast to beat. But in the future we expect this to be even faster. So just use quantum randomness locally. But if you exploit, for example, quantum entanglement, then you could create this common randomness. That means you have entangled the sender and the verifier, and based on this entanglement, you would have enough information about this common randomness. Once you have this, the same as in the seed example, you don't need to convey the random position anymore. You know about the conversion. The only thing you have to convey in this one would be then the tag value. We have done for this 4 cushions already. We worked already on that with some books that we published in this area. On the quantum one, you see the same people more or less that are giving this tutorial contributed to the quantum book. But what you also see is there's one book missing on Post-Shannon, and you know now what we have to do in the future. With that, I can just point you out to the literature. I only gave you here 3 different things that we did, especially one book chapter where we described our method that you have seen here in a nutshell. And with that, I would now to hand over to Rafael, who will give you the second part of the tutorial. Thank you very much.
Hello, now it's my turn to take over from Frank. In this part of the tutorial, I will present you some results on randomized identification and then subsequently on secure identification. This is not something I did by my own, but it's rather joint work with some colleagues of mine, most notably Holger, Boche and Deppe, who are also presenting some parts of this tutorial here, but also with Ono Günlü and Moa Kim, both from my group. Okay, so basically everything goes back to Shannon, who presented his fundamental or seminal work, A Mathematical Theory of Communication in 1948. And he was basically concerned with a communication problem, as you can see here. So this is basically a figure that is taken from the original paper of him. Yeah, so he's looking basically at a communication scenario where we have a transmitter and a receiver, and both parties, they want to communicate over a noisy channel here. Yeah, and he phrased basically the main problem that he was looking at as the following. He said that basically the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. So the important point here is that he kind of ignores any particular meaning or context or semantic of the communication, but rather he takes the information that is here as a message, and at the receiver side, he simply want to reproduce or decode the message that has been transmitted. So he's not concerned about the action or intention that such a message can have. Okay, so if I'm trying to formalize this a little bit more in the language that we are using, the communication model looks like follows. So we have a transmitter side, there's an encoder who takes a message M, encodes it into a code word XN, which goes over a noisy channel, which is abbreviated as W in this case, block length N, so we're using this particular channel W N times. After that, we have a noisy version, YN, which is received at the receiver side, and the receiver tries to decode the message that has been sent, M hat, and this should be done in such a way, obviously, that M hat is equal to M for a reliable and error-free communication. So this has been studied a lot, and first by Shannon, as I just mentioned, and the capacity describing the maximum transmission rate at which I can reliably transmit over that noisy channel is given by this expression. So this has been established by Shannon here. It is the mutual information between the input X and the output Y. And further, I may even be able to optimize over the input distribution. So I want to emphasize the point one more time that the important thing here is that I want to recover the exact message M, right? I don't care about the meaning of M or the intention or goal of M, what should happen afterwards here. I'm only interested in exactly recovering that message, okay? Another part that will be important throughout the whole tutorial is the question of randomness at the encoder. Here, in that particular scheme, or in this particular scenario, we don't need any local randomness and the encoder. What do I mean with that? Whenever I have a message M, there's a deterministic one-to-one mapping to a particular code word. Yeah, so no randomness, a deterministic mapping between the message and the corresponding code word. Another observation is in that particular scenario, the codebook size, meaning the number of different messages M that determines the rate here. The number of different messages scales exponentially. So we have 2 to the n r different messages available or possible. Yeah. So this is kind of the scaling of the codebook or the way how the rate is defined here. Yeah. So it is an exponential behavior. So this was basically the transmission problem where Bob really want to recover. So the receiver really want to recover the message. Okay, so whatever I'm sending here should be recovered here. In this particular scenario here, we are interested in another scenario or another application that phrase it like this, which we call identification. I think Frank already mentioned and motivated and introduced that scenario very well. But the main idea is that I want to rather in decoding the exact message. I'm rather interested in deciding whether or not, yes and no, a particular message has been sent. Yeah, for example, here Alice, she wants to send a message I, which goes over the channel to the receiver side, and the receiver side now just want to check whether or not, yes or no, a particular message, let's say J, has been sent, right? So here it's not the exact recovery of the particular message, but rather it's kind of a binary hypothesis testing situation, right? At the receiver side, I'm only interested in deciding whether or not a particular message has been sent. Okay, so let me also bring this in our framework here. The first part looks pretty much the same. We have a message, a transmitter, and encoder, which kind of encodes the message into a code word. It goes over the noisy channel W. At the receiver side, we receive a noisy version YN, but this time the decoder has the role that it should only decide whether or not a particular M hat has been transmitted. So this has been introduced, motivated, and also studied first by Alswede and Dück in 1989. And they were able to derive the identification capacity of that particular channel. And if you look at this formula, you will realize that here it is exactly the same expression as we have seen for the transmission capacity, right? Also here, we have exactly the same mutual information between the input X and the output Y. We are able to maximize or optimize over the input distribution. But if I'm only looking at this particular expression here, it is exactly the same quantity or expression, right? But you have to look into this a little bit more closer to see the difference or the huge advantage here, which is basically the remarkable property that the codebook size scales now double exponentially. Okay, and the transmission scheme, it was exponentially 2 to the NR. And for identification, we are able to transmit double exponentially many different messages, 2 to the NR. Okay, so we have an exponential gain, if you want to phrase it like this. Yeah, but what is important, what further differs to the previous case, is that now the encoder here at the transmitter side, we will need randomness to achieve this double exponential scaling behavior. So let me define or introduce a randomized identification code a little bit more in detail, just to give you an idea where the difference lies between a regular transmission code. I think some parts have been covered already by Frank in the beginning, but let me do it again so that we're on the same page here. Okay, so basically what we have here are N, the block length, capital N is the number of different messages, and then we have two errors, lambda 1, lambda 2. And then basically a code for me is a pair or a family of pairs, QI, DI. QI will be the input distribution or the randomized mapping from the message I to the code word XN, and DI are some kind of the decoding sets. Yeah, so basically what happens here is if I want to transmit message I here, I'm using the probability distribution QI to obtain the code word XN, right? So I want to transmit I based on QI, which may differ from message to message. I'm receiving a code word XN that goes over the channel, and it should fall into the right decoding area, right? And if it doesn't, so it's a complement here. So if I'm reaching outside that particular decoding error, I'm obviously making a decoding error. And this decoding error or identification error should be smaller than lambda 1. So this kind of gives me the type 1 error. It controls the quality of the right identification. And this is basically, the errors here are basically often caused by channel noise. But I also have, in this case, another error event, which is the following: that let's say I want to transmit a message, let's say J, and it now falls into another decoding set I. right? I'm transmitting J, but the receiver will identify or decide on the message I, so the wrong message. So we're doing here a type 2 error, identifying the wrong message. Yeah, so this is another error event. So compared to the transmission case by Shannon, where we only have one error event, here we have two error events where we have to take care of. Yeah, and I want to emphasize one more time, randomization is very important. So randomization is given here by these Q. These are taking care of the randomization. And just as an outline, of course, I can also do it without randomization, looking at deterministic identification codes, but this will be treated afterwards in a later part, I think. Okay, so let me compare one more time the different schemes here, because I think it's important. Message transmission, I want to recover the exact message. Identification, I only want to decide whether or not a particular message has been sent. Interestingly, capacity expression, if I'm only looking at the capacity expression, is exactly the same. Nothing, no change here as a first glance. But if you look closer into it, you will see that the scaling behavior of the message size changes. Here we have an exponential behavior. Here is a double exponentially behavior. Okay, so here you can say that going from message transmission to identification, we get an exponential gain here. Yeah, but if I'm merely looking at the expression, it's the same. But if you look closer into it, you will see that you actually have an exponential gain. Okay, so this was basically for discrete memory channels. And it's not surprising that you can also extend that to Gaussian channels. Yeah, so I only want to briefly mention how it looked like for Gaussian channels. Yeah, and this is as expected, as you can see. So with the Gaussian channel, I'm referring to an additive white Gaussian noise channel, which is basically given by this input-output relation. So we have the output yi, which is equal to the input xi plus additive noise ni. Okay, this noise is assumed to be IID and Gaussian distributed, zero mean variance sigma square. And we may have further an average power constraint on the input code words, right? So this is the average power constraint P. Yeah, and then it's not surprising that if I'm evaluating this capacity expression, IXY, you can show that for the identification, you also end up with the well-known 1/2 log 1 plus SNR expression for the capacity, right? So it looks pretty obvious, but you still have to prove it. So it's there's significant work behind that. It's not just plug and play, but you really have to prove it. But at the end of the day, it's exactly the expression you expect. Yeah. And I emphasize here, we do have both capacity, which means that we do have both achievability and converse, so that we have a precise characterization of the maximum transmission rate. Things change a little bit if I'm going to MIMO Gaussian channels, so multiple input, multiple output channels. Yeah. Input-output relation quite similar. We have an input, input X. We have an additional channel matrix H, output yi plus additive noise. And the channel matrix H is basically taking care of all channel coefficients between all transmit and receive antennas, right? So it's a very well-known and basic setup here that we're looking at. Again, we may have an average power constraint, P, and the noise is, again, Gaussian distributed zero mean sigma square for all receive antennas, right? So everything is pretty normal and as expected. And now I wrote that an achievable identification rate for this MIMO Gaussian channel is given by this one here. So maximizing over the input covariance matrix or the transmit covariance matrix. Then we have the log det I plus 1 over sigma square HQH transpose. So it is, again, the expression you would expect from the transmission capacity of a MIMO Gaussian channel. But the important thing is I want to highlight here or emphasize that it is only an achievable rate so far. Yeah. So we do have a coding scheme. We do have a proof that this rate is actually achievable. So we can transmit at this rate. But what is missing so far is kind of a converse or an optimality result. And with this, I mean that we can transmit at this rate. We assume or think that this is also the capacity, the best you can do, but we don't know right now, right? So converse is missing. So there's still the possibility that you may achieve higher rates. No one knows so far, since the converse or an optimality result is missing. Okay, this was basically the most fundamental results on identification. What I didn't talk about much is how the achievability or how the coding schemes actually work. This is done afterwards. Christian will talk about it a little bit more in detail about how these coding schemes work and how you actually do the identification. My part was rather, or my aim was rather to present you the results and to give an intuition or feeling what these things mean. What I want to do next is I want to combine these, or I want to incorporate some security aspects into this as well. Okay, and therefore I want to make a small detour, and I want to motivate or highlight what kind of security principles we want to use. And therefore I want to go back and look at how traditional security approaches work these days. Yeah, so this is again our very basic setup. We have the transmitter and message M. It goes to an encoder, you get a code word, noisy channel. At the receiver side, you get the message back, right? So what is the role of this encoder and decoder? It fights against the noisy channel, right? So the aim of the encoder is to encode the message M into code words such that they're good against the noise of the channel, so that at the receiver side, you can recover the right message, right? So basically, an encoder decoder properly designed for that particular channel will turn that channel into a kind of reliable bit pipe, right? So from higher layers, it may look as a reliable bit pipe. Yeah, you have a message M, you put it in there, you somehow transmit that over the physical layer. You don't care about the details. You only care about that at the receiver side, you get the message back. Yeah. This is kind of course, it's desired because you fight against the noise and you enable a reliable decoding at the receiver side. But you can also think of that this is kind of bad from a security perspective, because if you encode your message very well to fight against these noisy impairments of the channel, you will also do that for eavesdroppers or non-legitimate receivers, right? Some adversaries who may eavesdrop upon your communication. Also for them, you're turning their channel into a kind of a reliable bit pipe. If your information or communication or message that you want to transmit is confidential and you want to keep that away from non-legitimate receivers, what you nowadays do is based on cryptography, right? You're basically encrypting the message M, you're protecting it, then you send it over the reliable bit pipe, and at the receiver side, you have to decrypt the message. Yeah, you can think of that. This is kind of how I phrase it. It's kind of security on top, because on the physical layer, you do your encoding, decoding business to fight against the noisy channel. And on top of that, you employ your security mechanism, for example, by public key encryption. Yeah, so this works very well. But you can say that basically it's kind of a conditional security, because everything is fine and secure only under certain assumptions, like complexity or limited computational powers of the eavesdroppers. So it's always a fight against the good guys and the eavesdroppers, who tries to either encrypt the message very well, and the eavesdroppers try to break the system. So it's not ensured or fully secure, right? It's kind of conditional security. What we want to do is we want to look into something new, which is called, or what you call, information theoretic security or physical layer security. And that enables some kind of a paradigm shift for future system design. And it gives you the opportunity to use some kind of embedded security, which means that we want to integrate. We don't want to use realize security on top, on higher layers, but rather integrate that into the physical layer as well. Yeah. And yeah, this has pretty much a lot of advantages, but also new challenges. Yeah, so it merges both tasks on the physical layer, but it also gives you new challenges, because now we have to deal with channel uncertainty. We have to take care of that, interference, how many resources we have, what happens if we have adversarial attacks, and so on and so forth. Okay, so let me introduce the system model in more detail that we're looking at. This is known as the wiretap channel, and basically it is quite as expected. Again, we have a transmitter side, the message M is encoded, then we have the legitimate link as before, which goes over the channel W, and the legitimate receiver, let's say Bob, wants to recover the exact message. But now we also have an eavesdropper around who eavesdrops upon the communication. So whatever I'm transmitting also goes to another channel, to an eavesdropper who tries to extract or recover the message that has been transmitted. Okay, I mean, this is the best application here is, for example, in mobile communications. If you broadcast something over a wireless channel, it is received by legitimate receivers, but it is easily overheard by some other non-legitimate receivers as well. Yeah, so at the end of the day, we have two channels, W from X to Y and Y from X to Z, right? And what I'm looking at in the following is a passive eavesdropper, in the sense that this guy here only tries to eavesdrop upon the communication, but not tries to actively harm the communication. Okay, so now basically in the transmission setup, our goal or the tasks are twofold. At the one side, we want to reliably transmit that message M, and at the same time, we want to keep that message ignorant of the eavesdropper, or we want to keep the eavesdropper in the dark here. So what do I mean when I say I want to keep it in the dark, or eavesdropper in the dark, or keep him ignorant of that? I want to model that with information theoretic quantities. And for example, I could use strong secrecy, which tells me or requires you that the mutual information between M and the eavesdropper output Zn goes to 0. Mutual information kind of characterizes the information flow from the message M to Zn. Or if I phrase it a little bit differently, mutual information tells you how much Zn, the eavesdropper output, tells you about the message M. If this quantity becomes 0, M and Zn are independent of each other. And this means that if Zn is independent of M, the channel output that is received by the eavesdropper is independent of the message that has been transmitted, meaning that that channel output, Zn, doesn't tell you anything about the message because it's independent of it. This is something that is quite desirable. That is something we want to have. That is called strong secrecy, and I only want to mention that there are a bunch of other secrecy measures or conditions or requirements as well. And there's even a stronger notion of security these days, which is called semantic security, which is a strengthened version of this one here. So if you look closer into that one, you will realize that the message here, I didn't write it explicitly, but the message is assumed to be uniformly distributed. All possible messages are equiprobable. And for semantic security, you're also securing against a case that the messages have an arbitrary distribution. So they are no longer necessarily be equiprobable. Okay, anyhow, regardless of the secrecy criterion, it has been shown that whether I'm using strong secrecy, weak secrecy, or semantic security, I can look again at the capacity of that channel. And with capacity, I'm referring to, in this case here, the secrecy capacity. And this describes me the maximum transmission rate at which I can transmit the message M to the receiver, while at the same time keeping the eavesdropper ignorant of it, meaning that this criterion is satisfied. Yeah, the capacity here has been established and is given by this expression. So now we have a difference of mutual information terms. UY minus IUZ. UY is kind of the link to the legitimate receiver. IUZ is the link to the eavesdropper. And you see that the rate compared to the case of perfect of no eavesdropper, you now have a penalty here, more or less exactly to the channel quality to the eavesdropper. So this is kind of the price you have to pay to keep the eavesdropper ignorant of it. So this was secure message transmission. And now I want to extend these thoughts to the identification case. Yeah. So one more time, I'm comparing both scenarios. Secure message transmission, again, what we have just talked about. Message M is intended for Bob, and Bob want to decode the exact message. He want to recover the exact message. So he's asking, what is the message? Give me the right exact message. The same is true for the eavesdropper, right? The eavesdropper also want to obtain the message M that has been transmitted, right? And what the capacity is in this case, we have just seen the maximum transmission rate. On the other hand, if I'm trying to introduce a corresponding transmission setup for the identification case, it would look like this. I have a message here, M, at the transmitter side. The legitimate receiver, Bob, now wants to identify whether or not a particular message M star has been sent. And the eavesdropper overhears that communication, and the eavesdropper may also be interested in identifying whether or not a particular message has been sent. Right? So this would kind of be the analog system model for secure identification. Yeah, so let me summarize it one more time. For the secure identification case, what we want to do is we want to transmit a message to Bob. Bob want to identify that message. So Bob is interested in to decide whether or not an M star has been sent or not. And the eavesdropper should not be able to identify any message, right? So we want to enable reliable identification at the legitimate receiver side, at Bob's side, but we want to make sure that Eve is not able to do so. Yeah, also here, we are taking care, or we are employing randomized identification codes. And these are basically given as before. So if you remember the definition I've showed you in the beginning, these two conditions are the same. Right, so we have one, type 2 error. No, it's a little bit differently phrased here, only with one number. But again, it's a type 1 and a type 2 error. And now we have a third condition that kind of describes the security constraint. Yeah, and what is happening here is basically, if you look into it, you have two messages, J and I, right? And whatever decoding set you look at the receiver, you will see that the sum of these two is very close to 1 for any pair of messages. And this kind of models or requires you to design an identification code such that the eavesdropper is not able to properly identify the message that has been sent. Okay, so this has been studied by Alswede and Zhang in 1995. And they have established the secure identification capacity. And this is quite interesting and given as follows. So it has been shown that for this particular wiretap channel setup, the secure identification capacity is given as follows. It is either the regular transmission capacity if the secrecy capacity for message transmission is positive or zero otherwise. So let me plug in the results that we've seen so far for discrete memless channels. The secure identification capacity is either max mutual information IXY. Remember, this was the basic capacity of the point-to-point channel, right? The transmission capacity. So the secure identification capacity is either exactly the same if the secrecy capacity is positive, right? So this expression is valid for secure message transmission, yeah? No identification. This is if I'm able to securely transmit messages, then I'm getting this expression as a secure identification capacity. If I'm not able to transmit any secure messages, my secure identification capacity also drops down to 0. Okay, so this was everything was for perfect channel state information, where exactly know the channel W and also the channel Y. And this is particularly challenging because in practical systems, we will always have some uncertainty in the channel state information. Yeah, these stem from some very natural effects, like maybe we have a wireless channel who is very hard to estimate. So we may have further estimation of feedback inaccuracy. So from a practical point of view, you will never know the exact channel state perfectly. And therefore, we always have some uncertainty in the channel state information. Yeah. So even in the legitimate link, perfect channel state information is quite challenging. Even though Bob is a good guy and willing to cooperate with Alice, even in this case, you usually end up with some uncertainty in the channel state information. But of course, it becomes even worse for the eavesdropper, right? Because Eve is not a good guy. He will not share any information about the channel with Alice because this would hurt him, right? This would hurt the eavesdropper. He will not make his life even harder by sharing some information with Alice. Yeah. So assuming that we know the channel to the eavesdropper perfectly is even more questionable. And therefore, we should take uncertainty models for the channel state information into account. And what we want to do in the following, or what I want to present, are some deterministic uncertainty models. And I'm only saying or referring to that there are, of course, other uncertainty models that are based on statistical uncertainties and probabilities. But I will rather focus on deterministic models here, as I will introduce next. And in particular, I'm curious about the following uncertainty model for secure identification or secure message transmission. We have again the wiretap channel. And now I'm calling it a compound wiretap channel because I'm modeling the uncertainty as follows. Everything is as before, but now we have an uncertainty set S, which kind of characterizes all possible channel states. Yeah, so this capital S is a set that contains a whole bunch of different channel states that are possible. And what I know at the legitimate side, at the encoder and decoder, is I know the whole set S, so I know all possible states. But what I do not know is the actual realization that is happening. Okay, so I know all possible states that can trigger or govern my transmission here, but I do not know the precise state here that is happening. Yeah, and basically, it boils down to that I need to come up with an encoding decoding scheme here, or a security scheme that will work for all possible states simultaneously, right? If I know all states, but I do not know which one exactly I'm facing here, I should have a universal scheme that works for all these channel states. Yeah. And therefore, you also see that the secrecy condition here should be small, or the mutual information between M and the channel output should be small for all possible states, regardless of the actual channel that is happening. Okay, so if I'm interested in the secrecy capacity now, which means the maximum transmission rate over this uncertainty model, I have to admit that we don't know the capacity in all cases in a single letter way, meaning that a single letter description of the capacity is only known in very special cases like degraded channels or certain MIMO configurations. So for some cases, we know a single letter expression of the secrecy capacity, but in general, we do not know it. In general, we only have a multi-letter characterization. This one here. It looks complicated maybe, but if you look a little bit closer into it, you will recognize some familiarities to the regular secrecy capacity. We have again a maximization over the input. We have again these IUY minus IUZ quantities, channel quality to the legitimate receiver, Bob, minus as a penalty to the eavesdropper. What else do we have? We have an infimum of all channel states, because I have to prepare for the worst, right? So if I want to reliably transmit to the receiver side for any possible channel state, I should limit myself to the worst one. The same is true for the eavesdropper. I want to protect the message for any channel state, and therefore I should prepare for the worst. And in this case, of course, it's the best channel to the eavesdropper, right? Even if the communication conditions are best possible for the eavesdropper, then my scheme should be secure. Yeah, so here I'm taking the supreme. It's a multi-letter characterization, and with this I mean that I have the block length n everywhere, right? So I have here channel output n, and then I normalize by n. I'm taking the limit to n. But if you look a little bit into the structure of the expression, it is as you would expect from the secrecy capacity for the case of perfect channel state information. So you can ask the same question for identification, right? So I want to securely identify in the presence of channel state uncertainty. And this is something I call secure and robust identification, because I want to do it secure and also robust against the channel uncertainty. And here the capacity has again the same behavior or structure. The secure identification capacity over this compound wiretap channel is either the regular capacity to Bob, when I would ignore Eve. Whenever the secrecy capacity is positive, or otherwise it's 0, right? So we have exactly the same behavior as we have seen for the perfect channel state case. We either have the regular transmission capacity if the secrecy capacity is positive, or the 0 if the secrecy capacity is also 0. Exactly the same behavior. Okay, let me wrap up and present you one more time the most important takeaway messages here. Yeah, so I want to compare one more time the transmission scheme or the Shannon picture based on Shannon's seminal work compared to the identification picture from Alswede and Dück, where we have that particular application in mind where we want to identify a message. Yeah. So in the Shannon picture, the transmitter chooses a message M from a set of messages. It scales exponentially. So exponentially many messages. It goes over a channel, and at the receiver side, we want to recover the exact message. Compared to that, in the identification scheme, the transmitter chooses a message from a set of messages, which now scales double exponentially. Yeah, if you compare these two, if I'm fixing my block length n, 10, 100, 1,000, you will see that you have an exponential gain in the number of possible messages that you can transmit. Yeah? But to achieve this, we need some local randomness here to achieve this double exponentially scaling behavior. And at the receiver side, we only want to identify whether or not a particular message has been sent. Yeah, but the key message is here, we have an exponential performance increase. So how does it look like for the security? Again, both parts, the channel picture for message transmission and identification. For the transmission, the transmitter chooses a message M. Again, it's an exponential behavior up to the secrecy capacity here. And the secrecy capacity is the difference of these mutual information quantities, where you can clearly see that the eavesdropper affects the maximum rate. You get a penalty, and this is kind of what we expect, right? There's an eavesdropper around, we need to keep him ignorant, so there's some price to pay for it. Here we also have local randomness. So it goes over a channel, the receiver wanna recover the message, what is the message, and the wiretapper also wanna recover the message. In the new communication scheme of identification, the transmitter chooses a message M from a set of messages, which now scales double exponentially again. And surprisingly or interestingly, the capacity of secure identification is simply the maximum mutual information XY. So it's a regular, it has the same expression as the regular transmission capacity, as long as the secrecy capacity for message transmission is positive. Again, local randomness is needed. And also here, of course, the receivers and eavesdroppers' goals are different because they want to also only identify. Yeah. So again, here we actually have two effects that we see. We have an exponential increase in the number of messages. And in addition to that, we kind of pay no price for security. Because in the transmission scheme, you see that here's a penalty, right? Compared to the non-secure version, this is a penalty you have to pay to keep the eavesdropper ignorant. But here, you include security, and you're still achieving the same rate as without security. So we basically have no price. We have to pay no price for security in this case, which is quite remarkable. Okay, this brings me to the end of my part. And I'm done with that. And now I'm happily handing over to the next part. Thank you.
Thank you, Rafael, for your part of the tutorial. I will continue now with identification codes and deterministic identification. The contributors of this part of the tutorial are Holger Boche, who also will give the last part of the tutorial, Roberto Ferrara, he is a postdoc in my group, and he's working on the construction of identification code. Utsi Perik, he's also a postdoc in my group, and Mohamed Salarizedi, he's a PhD student in my group. They both worked on deterministic identification codes. Rafael already gave an idea about the difference of transmission and identification codes. And he showed you how the information theoretical analysis is done. I will shortly repeat this difference and then come how we can construct also codes for this. So in transmission, we want to know which message is sent. So Bob wants to know which message is sent by Alice over the channel. Therefore, he constructed decoding sets and he looked in the decoding set and then decided which message has been sent. Therefore, we can look at the average error here or at the maximum error, which is denoted here. In both cases, we know by Shannon that the transmission capacity C is the best achievable rate, log m over n. is a well-known formula by Chen. And we have somehow two kinds of errors, but both are bound by epsilon. So if we send xm and we land here in a decoding set dm, then we have a correct transmission. If we send some other x and land here in this dm, then we have somehow a false positive error. The other is if we send something and land in something where we cannot decide it, what message it is, this is false negative. But both errors are included in this epsilon here. In identification, the situation is different. Bob just wants to know if a special message is sent or not. So he has his message I prime, and he wants to know if Alice had sent I prime yes or no. So finally, he accepts the message or he rejected. For this reason, we can have overlapping decoding sets. Because Bob somehow selected one of these decoding sets and look if the message which is received is inside this decoding set or is outside. Therefore, he decided that the message is sent or is not sent. Here again, we have two types of errors, but this time they are bounded differently. So first, if we send message xi and land in set di here, and Bob decided for the set di that his message was sent, this is a correct transmission. Then there's a type 1 error. That means we send something, but it lands because of the channel error, in the wrong decoding set. And Bob decided that his message was not sent, even it was sent. That's false negative. Another thing could be that we send message xj and we land in the decoding set dj, but because of our decoding scheme, di overlaps with dj. And Bob decided that his message di was sent, even that the sender sends dj. So this is type 2 error, that's false positive. It comes from the decoding scheme. And now the identification capacity is the best achievable rate log the cardinalities of the identities over n. You see you have this double exponential growness here. And the very important thing is what Rafael already told you. Shannon capacities for transmission is equal to the identification capacity, but we have this double exponential growness. What happens for a noiseless channel? If we have a noiseless channel, then we have only errors of type 2, because we have no channel error anymore. We have to be careful. Asymptotically, we have 0 pairwise overlap, but exponentially many overlaps. And if we have small pairwise overlaps, that doesn't mean that we can small pairwise distinguish these sets. And what is very good, the separation coding for noisy channels is optimal. That means if we have a strategy, a coding for the noiseless channel, then we can use a channel code and use it for a noisy channel. How is now an identification code constructed? The idea, already Frank give you an idea about this, are tag codes. The idea is now we use a transmission code, and we do the following. We have a transmission code which can transmit M messages. So at the sender side, one message is now chosen at random. And for each identity, we have a function, the so-called tag function ti, which is a function from m to q. So if we now we got the random chosen message and the identity we want to send. So we choose the function ti and look at the value of ty for m. And then we transmit m and ti of m over the noisy channel. Thus, the decoder receives some m prime and some t prime. Let's assume he is interested in I prime. Then he looked at then he calculated ti prime of m prime. And then he compared with t prime. If this is equal, then he decided that his identity I prime is sent. Otherwise, he rejects this. This is the main idea of an identification code. The very interesting thing is that ti of x can be sent without using capacity. So that means this part of the code have capacity 0. If we now have a capacity achieving transmission code, we want to know which properties we have to have for a tag code that we achieve the identification capacity. So a tag code IMQ omega over m is a collection of I functions, so I is a number of identities, from m to q with pairwise overlap at most omega. So we need a tag code which is such that the size of I is exponential in m, because we want to have this double exponential growness of the code. The bits of the output log q have to be sublinear in bits of the input log m. And furthermore, of course, epsilon should go to 0. Remember, this epsilon is error of the first and error of the second kind. How we can construct such tag codes? We can use error correcting codes. We take just an error correcting code of block length m. I is the size of the code, and d is the distance of the code. That means our code have I code words and m symbols of size q. And we can use it as a tag code. Let's assume now we want to send message I, then we message I, then we choose the column CI, so the code word CI, and if randomly selected, we select the message M, then we use here CIM and send this over the channel. So that means this error correcting code gives you a tag function. What properties do we need? It was on the slide before. We need that log I over log m goes to 1, because then we have this double exponential growness. And we need that log q over log m goes to 0. And furthermore, we need that d over m goes to 1. We can estimate the number of identities simply by the Gilbert-Bashamov bound. So that's a greedy construction, and I think it's well known how to get this bound here. And we can estimate this bound by q to the m over 2 to the m times q to the d. And now, because d is equal m minus omega, we know that this is equal q to the omega over 2 to the m. Now, if we choose omega equal to 2 over log q times m, then we have indeed that I is bigger than 2 to the m. So we have this double exponential growness. And epsilon is less or equal than 2 to the log q. That means if q is growing, epsilon goes to 0. Now we have to find some kind of error correcting code with these parameters here. Then we get with this error correcting code automatically such a tag code, and we can use it for an identification code. And the first who showed that such code exists were Verdu and Wei. They take a concatenated Reed-Solomon code, and this code is capacity achieving. Unfortunately, we analyzed their codes, and for application with finite lengths, it was not usable. Then you can, of course, look at other codes. For example, in a bachelor thesis, one student looked at turbo codes, but it turns out that these codes doesn't work. They are not capacity achieving and also not good for finite length. What we did then is we looked at Reed-Muller codes. These are also capacity achieving, and they have a better performance than the Reed-Solomon codes. At the moment, these are the best we found. But of course, we can look at other possible codes, like polar codes or any other randomized codes. That will be the next goal. I shortly come now to the secrecy of identification. As Rafael already pointed out, somehow you don't have to pay a price for secrecy. Because if you look at the two parts of an identification code, this is the random part and this is the tag part, then this U is not interesting for the wiretapper. Only this part, the tag part, is interesting for the wiretapper. So that means secret identification is still the non-secret identification capacity, as Rafael shows you, even if the secret transmission capacity is significantly lower. But it doesn't have to be zero. If the secrecy capacity is zero, then we also cannot send secret identification message. Now we try to implement the secret identification codes. The first idea we have, we use a paper of Boche and Wiese. They use mosaics of combinatorial designs to achieve information theoretic secrecy. They showed that they can achieve it for the seeded wiretap scenario. And the idea is they use the function induced by such a mosaic of combinatorial designs as a secrecy function. We combine this with our identification Reed-Muller code and analyze this code. And there, with this method, you get an information theoretic secret identification code. As you saw, randomness play a very important role in identification. So in principle, the achievable rates depend only on the size of common randomness. So if non-transmission source of common randomness are present, the identification rate increases. That means if we have additional common randomness, we can increase the identification capacity. You don't have such a behavior for transmission. However, the identification capacity is zero if we cannot transmit anything. Then identification is also not possible. And there's a claim that the identification and common randomness capacity are always equal when the transmission capacity is non-zero. This is already proved for the discrete memberless channel by Alswede. Possible applications for identification. So one thing is we can combine transmission and identification. For example, we want to do a communication with a lot of receivers which are listening to the same channel and they have some feedback. That means we first send an identification message and then someone signals it's me, and then we send something to this receiver. The other thing we can use is what Alswede and Chai already showed, is we can use identification and transmission for watermark. Pure identification code we can use for for scenario with low latency, where only a few outcomes among many others are relevant, like for car-to-car communication. The big advantage is that we can use already implemented codes. If you are interested to go deeper in this topic, there's the paper about the Reed-Muller identification. Here, practical implementations of identification. This paper is a performance analysis of this original identification code of Verdu and Y. Furthermore, Günlo, Gliva, Schaefer, and Sidorenko gave some code construction and further bounds for identification codes via channels. Now we will look at the case if we have no randomization at the sender. That means the encoder has to use deterministic mapping for the coding. And this is a simpler implementation because we don't need a random resource. And still, the achievable rates are higher than in transmission. You will see this later. And this model is suitable for molecular communication. So it's related, for example, to olfactory-inspired MC system or to cancer treatment and target drug delivery. Normally, for the discrete memberless channel, it doesn't matter if we have a deterministic encoder or randomized encoder. In both cases, we got the well-known Shannon formula and the Shannon capacity. For identification, it's different. So what will we do at first? First, we look at the discrete memberless channel. And we will establish the DI capacity with and without power constraint. And we will see that in this case, we again use the same scaling as Shannon did, the traditional one with 2 to the NR. And the analysis to calculate the capacity combines technique and ideas from the works by Yaya and Alswede. So Yaya was the first one who had the idea to look at a receiver who didn't ask for the message, but asked if a message is received or not. And he looked at deterministic encoding. He used it for a communication complexity model. When Alswede saw this work, he got the idea of randomized encoding and find out his well-known formula with a double exponential growness for identification, for which he get IEEE award. How is now a DI code for a DMC defined? So here you see I included this LNR. What is this LNR? In this LNR, I always write down the scaling. Later you will see why. So that means for identification codes, I would have here 2 to the NR if we do it with randomization, but without randomization, I have the same scaling like for the transmission case. Again, we have the block length n, and we have the 2 arrows, lambda 1 and lambda 2, arrow of the first and arrow of the second kind. Now we have a system of code words and decoding sets. And UI is an element of x to the n, and the decoding sets are subsets of y to the n. And we immediately look at some input constraint. That means we have a cast function phi from x to 0 to infinity, to a positive value we have here. And we look at the average constraint here. So a is also a positive number. So the average costs are bounded by a. And here you see, as before, also for the randomized case, we have the error of the first kind, which comes from the channel, and the error of the second kind, which comes from the coding scheme. So the first theorem we have, if we have a DMC with distinct rows in the channel matrix, then the DI capacity under input constraint is given by the maximum over the expected value of the cost constraints of the entropy of X. From this result, I will give you the idea soon how it is proven. Directly follows a theorem of Alswede and Dück. It was just it was just provided in their first paper, but they didn't prove it. So they say for a DMC with a channel matrix with distinct rows and the scaling 2 to the NR, the DI capacity is given by log of X. It was just a remark in the original paper. And it's a consequence of our result for with cost constraints. Just look at phi max. That means we have no cost constraint. It's just the sum of all costs. So that's not possible that we can exceed this. Then this maximum gives the entropy of X. And we choose every distribution on the set from 1 to X. And of course, this is a uniform distribution. And we know if we choose the uniform distribution here, then the entropy of X is the logarithm of X. So the result follows easily from the result with cost constraints. How can we prove the theorem with cost constraints? The first thing, what we use is a lemma. This lemma says if the rate is below the entropy, then there exists a set of code words VI such that VI belongs to the typical sequences, and the distance from Vi to Vj, if I is not equal to j, is greater equal n times epsilon. And the third condition which holds them is that the cardinality of this set here is greater equal than 2 to the n r minus some theta. And using this, we can provide the following coding scheme. The encoder, given a message I, transmits xn equal to vi of the set we have in the lemma before. And the decoder is just a typical decoder. He just choose it as dj all yn such that yn and vj is jointly typical. And the error analysis is done as follows. The error of the first kind, we can show that it goes to 0 by a standard type class argument. For the error of the second kind, we need a theorem of Alswede for conditional type intersection, the conditional type intersection lemma. You have this lemma here. It's from Alswede in 1980. So it says just if you have a matrix from xy of a DMC with distinct rows, then for every xn and xn prime in the typical set, such that the distance is bigger than n times epsilon, the cut of the typical set of y conditional on x and the typical set of y conditional on x concerning x prime divided by the typical set concerning xn is lesser equal e to the n times g of epsilon for some sufficient large n and some positive function g of epsilon, which is independent of n. Yes, this lemma was used to show that the error of the second kind goes to 0. The converse is very easy in this case. For randomized identification, you see in Rafael's talk that the converse is very difficult. But for discrete identification, it's not so difficult. At least in this case. Here you just have to show that distinct messages have distinct code words. Otherwise, the error of the first kind or the error of the second kind doesn't go to 0. So if you have I1 not equal I2, then it follows that UI1 is not equal UI2. This is the main step for the converse. What we do then is we just estimate 2 to the NR by the cardinality. It's just the cardinality of the set x to the n. And here you have all sequences such that the average cost constraint is not bigger than A. And this can be estimated because of typicality here by this, and then we are already ready, because this gives you this formula here that R is lesser equal than h of x plus alpha n. Now we go to the first continuous channel. We look at the Gaussian channel. There we will give you some lower and upper bounds on the DI capacity for average cost constraint. And we will look at fast fading and slow fading. And you will see we need another scale, not to get 0 or infinity, to get a positive value. And you will see that this scaling is different. It's in between the other two scaling we used before. It's 2 to the n log n times r. How is now a DI code defined for a continuous channel? So we will look at the Gaussian channel and the Poisson channel. Both are continuous channels. You see here that in both cases we need this scaling here. That's somehow a spoiler, because otherwise we get 0 or infinity. Again, we have a deterministic code. So code words are element of xn, and the decoding sets are subsets of yn. And again, we look at some maximal input constraint at some average input constraint. And as you know already, we have the error of the type 1, which comes from the channel, and the error of type 2, which comes from the decoding scheme. Instead of looking at the Gaussian channel, we look at some more general channel. We look at the fast fading channel. Here you see the picture here, and you see fast fading is defined as follows. As output, you get G is X plus Z. And for slow fading, you get this letter Y. So YT is equal G times XT plus ZT. And again, we look at this power constraint here. And of course, the noise is Gaussian. And here you see before we have these two scalings for transmission and this scaling for identification. And you will see later we will in between these two scaling. You see it here. That's the first result. It's for fast scaling. So the DI capacity in this case is bounded by 1/4 and by 1 if you use the scaling here. And here, just as a reminder, if we have the scaling like for transmission, then we get infinity capacity. If you use the scaling like for randomized identification, then we get here 0 capacity. Of course, the standard Gaussian channel is a special case of the fast fading channel. And for the achievability, we just use sphere packing of radius n to the 1/4. And then we got 2 to the 1/4 times n log n code words. That's the achievability part. So we need a dense sphere packing arrangement with radius square root n epsilon n, and we use the Minkowski-Lavka theorem that the density is big enough. And therefore, we can upper bound the rate in this way, and this term here goes to 1/4. Now we have to prove also, or ensure also, that the error of the first kind goes to 0 and the error of the second kind goes to 0. This is done by the Chebyshev inequality. So the condition 1 and 2 means that epsilon n is equal a over n 1/2 times 1 minus b for b bigger than 0, and therefore epsilon goes to 0. The converse is also similar to the deterministic case. Again, the idea is here that if two code words are too near together, then it is not possible that the error of the first kind and the second kind goes to 0. Remember, for the discrete memories channel, we can say that we don't have two code words which are the same for different messages. And here, the distance for different messages cannot be too small. So in this case, cannot be smaller than n times epsilon n. Otherwise, we have this sum here, and that means it's not possible that the error of the first kind and the error of the second kind goes to 0. And the tight upper bound requires epsilon n large as possible. The kappa n tends to 0, of course. And then again, we get at epsilon n, it's a to the n square, and therefore epsilon goes to 0 as n goes to infinity. Now we want to look at the case of slow fading with positive fading coefficient. Then the DI capacity is just bounded again by 1/4 and by 1. And the proof is very similar to the case for fast scaling. Again, I want to remind you, if you look at the traditional two scalings for randomized identification and for transmission, we get infinity and we get 0 here. The result for the Poisson channel, so again, we provide some lower and upper bound for the memoryless discrete time Poisson channel and to both average and peak power constraints. And again, you see, I spoiled you already with the definition before. We have the same scaling as for the other continuous channel for the Gaussian channel. Here we have, again, we have here a molecular channel, and we have an encoder which put in the UI in the molecular channel, and it puts out a Y, and we have here a decoder who want to identify if the message is J or not. And here are the concrete definition. So the YT here is Poisson distributed with lambda plus rho plus UIT. And the lambda is the expected number of interfering molecules. And rho x is the expected number of observed molecules due to the relays by the transmitter. Here it's Alice. Y is the output vector, and we consider a maximum power constraint and average power constraint here. And then if we, the error probability, if we send UI that we receive Y is given by this product here. And you see, again, we get a bound for the deterministic Poisson channel with expected interference lambda and average and maximal power constraint, and the scaling here, we get the bound 1/4. In the upper bound, it's different, like for the Gaussian channel. We were not able to show 1, but we can show 3/2 here. And the idea, we use again sphere packing of radius square root, fourth root of n. So we have 2 to the 1/4 n times log n code words, and therefore we have this bound here. So we do some dense sphere packing arrangement with a radius square root n epsilon and n, and like in the Gaussian case, we use Minkowski-Lavka theorem to guarantee a density greater or equal to the minus n. And with this, we can upper bound the rate by this expression here. And for n to infinity and b to 0, this expression goes to 1/4, where the a here is the minimum of the average power constraint and the maximum power is power constraint. The small a is constant and b is an arbitrary small constant. And again, we also have we can use Chebyshev's inequality to show that the error of the first kind and the error of the second kind is bounded as follows. And because of this, epsilon is equal a to the n 1/2 times b minus 1. And the error of the first kind and the error of the second kind goes to 0. For the converse, we have to do a very similar calculation again. So we have to show again if we have two different, that it's not possible to have similar code words for different messages. So they are not too near to each other, as in the Gaussian case. So if you have code words ui and uj, where I is not equal j, and we look at the case that this is greater epsilon n, then we get a contradiction that the error of the first kind and the error of the second kind can go both to 0. And here you see how we got the upper bound. So we have this estimation here, and therefore we can upper bound the rate by this expression. And if you look at the case of n goes to infinity and b goes to 0, then this is bound, this goes to 3/2. Here you see again that there are more than the scaling I showed here. So you see here is the traditional scaling for the transmission of the discrete memless channel and the Poisson channel, or discrete identification for the DMC. And here's our scaling, what we found here for the Gaussian channel and the Poisson channel if you do deterministic eigenidentifications. There's also this scaling here for covert communication. If you want to hide that you even communicate in front of a wiretapper, so no one can say if you communicate, and you can do this covert identification. Yes, and you have this scaling here. Here you see the scaling for randomized identification. And in the next part of the tutorial, you will see if you have the deterministic identification with noiseless feedback over the Gaussian channel, then you get, then you can look at every scaling and the capacity will be infinity. But this will be done by Holger in the next tutorial. Now we come to part 4 of our tutorial. This part is about identification with feedback, and identification via the broadcast channel. For some health reason, Holger Boche cannot give this talk in time. Therefore, I will present his slides now. The work for this tutorial were done by Holger Boche himself, by myself, Rafael Labidi, she is a PhD student at the chair of Holger Boche, Utsi Perek, he is a postdoc in my group, Johannes Rosenberger, he is a PhD student in my group, and Moritz Wiese, he is a postdoc at the chair of Holger Boche. Moritz, Rafael, myself and Holger worked on the part of identification with feedback. Utsi, Johannes, and myself worked on the part about the broadcast channel. So we heard in the last part about deterministic identification. Now we look at deterministic identification in the case by adding a feedback link. We assume that this link is noiseless. That means every time a symbol is received by the decoder, the encoder sees what is received. This model for the discrete mammalist channel was first considered by Alswede and Deppe. We consider this together with Rafael and Holger and Moritz for continuous channels. But first, let's look at the case of the discrete mammalist channel. For the discrete mammalist channel, we get the following result. The capacity of the identification feedback capacity is equal to the maximum of X of the entropy of the channel conditional of X if the capacity of the channel is positive. It's 0 if the channel is noiseless or the transmission capacity is 0. Why we have this strange behavior? Again, I should remark that again we have this double exponential growness. So what we denoted in the previous talk by this L, the scaling, we have this double exponential scaling, and in this double exponential scaling we have here the entropy if the transmission capacity is positive, and otherwise we have 0. The reason is, what comes later is really that if the channel capacity is positive, we can create common randomness by using the feedback link. We cannot do this if the channel is noiseless, because there is no randomness in the channel. And we cannot do it if the channel is 0, because then we cannot transmit anything. We have this very special behavior because in message transmission for the discrete mammalist channel, feedback does not increase the capacity of the DMC. But here we show feedback allows a double exponential growth of the numbers of identity. Furthermore, in message transmission, noise decreases the transmission capacity. And here we see that noise can increase the identification feedback capacity. Let's look a little bit deeper at the model. So here we looked at the very general model. So we have an encoder, and he encodes a message M and send it over the channel with noiseless feedback. ZT denotes the noise. And we assume that ZT is drawn from a non-discrete distribution P. And we denote this channel by WP. And again, of course, we look at identification. So Bob will make the decision if M prime is sent or not. What we need for this, because we look at a very general continuous channel, we need the Lebesgue decomposition. What does it say? If P is a probability measure with the cumulative distribution function with cumulative distribution function f, then there exists a triple of cumulative distribution functions D, A, and S, such that D is discrete, A is absolute continuous, and S is singular continuous. And non-negative numbers, PD, PA, and PS, which satisfies that PD plus PA plus PS is equal 1, such that F is equal PD times D plus PA times A, PS times S. So we can really decompose this function in the discrete part and in the non-discrete part. So if F is not discrete, then P and F are called non-discrete. This phenomenon we have, for example, for the Gaussian distribution. How does now feedback encoding functions look now? So a feedback encoding function is a family F of real valued functions. F1 is an element, is a real number, and then Ft goes from Rt minus 1 to R. And T is an element from 2 to the n. That's the reason the sender always knows what the receiver have received and make a strategy dependent on the receive symbol of the receiver. Now for gamma greater equal 0, we denote by F bar and gamma the set of feedback encoding function satisfying the average power constraint, this one here, for all y1 to yn minus 1 in R to the n minus 1. And we denote it by Fn delta if this feedback encoding function satisfies the peak power constraint. So the cost, we looked here at this cost for n, all t in 1 to n and all y1 to yt minus 1, a vector in R to the t minus 1. Now, what is an identification feedback code for WP under average power constraint? So if you look at this channel WP with a non-discrete white noise, and lambda 1 and lambda 2 are non-negative reals satisfying that its sum is smaller than 1, then an n lambda 1 lambda 2 deterministic identification code for WP, which average power constraint is a family of pairs Fi Di, such that Fi is in the set F bar and gamma. The Di's are subsets of Yn. Again, different to the transmission, we don't have the condition that the Di's have to be distinct. And here we have the error of the first kind, and here we have the error of the second kind. The achievable transmission feedback rate is defined as follows. So if gamma is greater or equal 0, a number R is called achievable message transmission feedback rate with average or peak power constraint gamma if for every lambda and delta greater 0 and sufficiently large n, there exists a message transmission feedback code for WP satisfying log m over n is greater or equal R minus delta. And the maximum achievable rate is called the message transmission feedback capacity with peak and average power constraint gamma. The first theorem said if we have a lambda in between 0 and 1 over 2 and gamma greater 0, if WP have a positive message transmission feedback capacity, which average power constraint gamma, then there exists a block length ns such that for every positive integer n and every n greater equal ns, there exists a deterministic nn lambda 1 lambda 2 identification feedback code WTP with average power constraint gamma and with lambda 1 and lambda 2 lesser equal lambda. So without feedback, the number of identities scales, as you see in the part before, as n to the nr in the block length n. And here, regardless of the scaling, for the identification feedback capacity, it holds that the capacity is infinite because of the theorem here. So you can choose any scaling, even the double exponential, triple exponential, and so on, and always the identification capacity stays infinite. The same holds also for the peak power constraint. You see here, this is exactly the same, only with peak power constraint. How can we prove this? To send a message I, we prepare a set of coloring functions or tag functions. In the talk before, I called them tag function, fi, known by the sender and the receiver. You see here this tag function. Here, these are the number of messages from the transmission code, and they are hashed to this part here of the colors or tags, however we call it. And first, we send x1, x2 to xn over the forward channel. We generate a random variable, y tilde, equal to k of y. And the cardinality of L is used to compute the rate of the identification feedback. And C, this is a pair of UI and UJ and DJ, is an NM 2 to the n minus delta code. And now what do? We send first this UFI of KY, and we send this KY over the channel. That means we can generate a 2 times n and lambda 1, lambda 2 identification feedback code. So with the first part, we generate the feedback, generate the common randomness between the sender and the receiver. And with the second part, we send the tag or the coloring. Now the receiver, he received this KY and he put it in his function. For example, in this case, he asked, is I prime sent? He compared the received number and put in KY in his function and compare this. If this is equal, then he accepts it and decided that I prime is sent. If it's different, then he rejects it and decided that I prime is not sent. So you see, this coding scheme allows to generate infinite common randomness between the sender and the receiver. The reason is really the noiseless feedback. And we use the noise of the channel to share infinite common randomness between sender and the receiver. And this can be used to get an infinite identification capacity with feedback. And the size of this random experiment can be used to compute the growth of the identification rate. So this construction somehow follows the construction of Alsweder and Dück, but they cannot generate infinite randomness, only limited, because they looked at the discrete mammoth channel. To achieve the maximal possible rate, the length of the transmission code could be negligible. So that means the number of channel uses needed for the common randomness generation, usually in the discrete mammoth case, Alsweder and Dück use square root of n for the transmission of the tag or the colors. And it does not matter in our case, since the capacity is infinite. Now let's look at the scaling. Now we denote it by phi. In the part before it was denoted by L. The identification feedback rate for WP is called achievable, and phi with respect to phi and with average or peak power constraint gamma. If for every lambda between 0 and 1/2, there exists an ns of lambda, such that for all n greater equals than n of lambda, there exists an n phi and r lambda deterministic identification code for the channel WP with average or peak power constraint. So that means independent of the scaling. So the deterministic identification capacity of the channel with the rate function or the scaling phi and with peak and power constraint is the supremum of all achievable rates. And that means we can use any scaling and we always get infinite. So examples, for example, the standard scaling is 2 to the x, and for identification, randomized identification over the deterministic channel, we have 2 to the x. As a corollary, we get let phi be an arbitrary rate function and let gamma greater equal 0 if the channel with non-discrete additive white noise have positive message transmission feedback capacity with average power constraint, then the capacity is infinite. If WP has positive message transmission feedback capacity with peak power constraint gamma, then again the identification feedback capacity is infinite. So in contrast to message transmission, feedback has really a dramatic different effect. So in our first paper, we just consider the Gaussian channel. So we consider a normal distribution P with 0 mean and variance sigma square greater 0. And the message transmission capacity under average and peak power constraint is positive for all gamma. And here we just send one symbol to create infinite common randomness. And without feedback, the number of identities is positive and finite with respect to the scaling 2 to the x. Here again, we summarized the scaling and for what it's used. Perhaps you saw it already in the first part, in the third part. So here for transmission, we have the scaling 2 to the nr. For deterministic identification, it's 2 to the n log nr or nnr. For randomized identification, it's 2 to the nr. And it's infinite deterministic identification with noiseless feedback. So non-discrete additive noise channels, they have infinite deterministic identification capacity regardless of the scaling. And for deterministic identification feedback capacity over the DMC, if the DMC is noiseless, then the deterministic identification capacity is 0. And if the DMC has positive capacity and is not noiseless, then the deterministic identification feedback capacity is positive, but finite with a double exponential scaling. The reason I already told you several times, uniform random experiments on arbitrary large finite sets cannot be generated from a finite number of channel outputs of DMC. And randomized encoding allows to increase the identification capacity over the DMC with respect to the double exponential rate function. That means if we have a positive capacity of the channel and we can use the feedback to generate randomness, then we have this double exponential growth. So if you want to go deeper into this, there is the pioneer paper of Alsweder and Dück, where they look at the channel with feedback and discover the new capacity formula. The special case of the Gaussian channel you can find in this paper here, and the identification over additive noise channels in the present feedback you can find in this paper here. Now we will look at identification over broadcast channel. So we looked here at one encoder and we have two channels here, and on the two decoders, both decoders want to identify and know if a special message is sent or not. And we looked at the more general case, at the compound channel. In this case, before the transmission starts, state is chosen, and we have a set of channels, and this channel is used during the whole transmission. And now an N1 identification code is a family of triples, QI1, I2, and decoding sets DI1 and DI2. This is for the first decoder. This is for the second decoder. For EI1 going from 1 to N1 and I2 going from 1 to N2. We can look at the maximum and the average case. So we define an NN, N1, and 2 lambda code for the channel pair W1 and W2. First, there's the work of Alswede. This was the first result. You can find it in his paper, General Theory of Information Transfer, updated 2008. Here he assumed that the message distribution is unknown. And we have to, in this case, he maximized over the messages, and QI1, QI2, DI1 is an NN1 lambda ID code for every W1S. S is in here in the set of states. And Bracha and Lapidov, they consider the uniform message transmission. And here it's irrelevant that the messages are random and no more randomness is needed because they average over the other channel, over one of the channel. Let's look at the result of Bracha and Lapidov. They gave their result for S equal 1. So it's not a compound channel really, it's a normal broadcast channel. And here we can also look in the case, we can look at the degraded transmission. There we have this capacity region here, you can see here. This is a subset of the capacity region of the channel considered by Alswede. And this is again a subset of the channel region, of the capacity region considered by Bracha and Lapidov. Now we looked at the general case. That means we have an arbitrary state set here, and we have an average power constraint here. So we looked at the Gaussian case, and here you see the rate for the degraded transmission, and here you see for symmetric channels. So here you have this rectangle here for CIDA. And for CIDM, you have this curve here. This is in our paper, Identification over Compound MIMO Broadcast Channel. And we also did some generalization to quantum channels. We didn't talk about quantum identification at all in this tutorial. There one have to be a little bit careful because identification can be generalized in several ways. Because you can imagine that for quantum channels, you cannot just take the definition like it is, because if you have many receivers, you have the problem that in the quantum case, you can just measure once. And when you have measured, no one else can measure again because the qubits the state is destroyed somehow. And therefore you define simultaneous identification. In this case, only one measurement is done, and the result of the measurement is forwarded to several receivers. And depending on this result, the receivers make a decision. And the normal, what is called quantum identification. In this case, we have just really one sender and one receiver. In this case, we can do one measurement and decide on this measurement. And for classical quantum, For the classical quantum capacity, we have the surprising result that simultaneous identification and quantum identification has the same capacity. And at the moment, there's no counterexample found that the simultaneous identification and the quantum identification is different. Now let's look at the case for the MIMO. Here we only look at the case when S is equal 1, and we calculate the capacity for the MIMO channel. So we have tau transmit antennas, and we got this weight region here. So if you want to go over this or more deeply learn about this, because I was going very fast through this multi-user case, you can look at our papers. So there's one paper, identification over the compound MIMO channel. Then there's this paper, of course, of Bracha and Lapidot. Also, the PhD thesis of Bracha is very helpful to understand identification via broadcast channels. There is a paper of Alswede on general theory of information transfer, updated. And then there's a channel where the degraded broadcast case is calculated in Billig and Steinberg's paper. Furthermore, there's a paper of Verboven and van der Meulen about the capacity bounds for identification via broadcast channels that are optimal for the deterministic broadcast channel. Thank you very much for watching our tutorial. I hope we could teach you something. Unfortunately, I had to take over Holger Boche's slides part of the tutorial at short notice. Therefore, I was not so well prepared for it. We will be happy to answer any question you may have about the tutorial. You can also contact us personally via email. Many thanks to the organizers of the ICC for giving us the opportunity for this tutorial.